I hope everyone can see my slides.
Yes.
Yeah. Okay. All right. So now we will continue with the techniques part of this module, and today we'll focus on correlations. So I'll just go through this one by just a quick recap here. We looked at the data. This is how it looked like. This is the firing rate from one of the two neurons that are given to you in this data set. We asked the question whether the neuron here is following a rate versus a temporal coding scheme. To answer that, we talked about probability and random variables. And we defined what a random variable is in terms of the sample space, sigma field, and a probability measure. Then we found, so we created a random variable which was just the total number of spikes within some interval, which is given here, baseline and stimulus periods. And this is how the random variable was for the 76 trials. So when I did the experiment 76 times, this is the value of the random variable. And from this, I got the probability mass function of the random variable during the baseline and stimulus period. These are experimental. Then I asked the question that if a random variable is indeed, if the neuron is firing indeed randomly, what should be the shape of the probability mass function? And, under fairly general conditions, turns out the probability distribution function follows what is called a Poisson distribution. Okay, so then I asked whether my neuron here is following a Poisson distribution or not. And turned out, at least in the first glance, that it seems to be quite Poisson-like. Then I further asked whether this question by asking what is the distribution of the inter-arrival times of spikes, the ISI or interstimulus interval distribution. And for a Poisson random variable, the inter-arrival times follow an exponential distribution. And in my case, the PMFs indeed look like exponential, giving further, evidence that the neuron is firing in a Poisson-like manner. Okay, so that's that. Now we are ready to move to the next section. Are there any questions about the previous part, or can I move on?
I have a question regarding the previous part.
Yeah.
How you calculated ISI?
What?
How do we calculate ISI? Is it just first of all for
Yeah, so if you look at this program, Get ISIs, it will tell you how to do it. It's actually very straightforward. If you, it's like a 10-line, a very simple code. Sorry, here. So here you have the raster plot, right? So what is given to you is just for each trial, what are the spike times? So within a trial, let's say the second trial, you find there are 6 spikes. And then all you are doing is spike 2 time minus spike 1 time, spike 3 time minus spike 2 time, spike 4 time minus spike 3 time. So you'll get 5 ISIs from that trial. If there, yeah, and then you just concatenate that, you just keep doing that. If there is only one spike, you don't do anything, you leave it alone. If there is more than one spike, then if there are n spikes, you will get n minus 1 ISIs.
so then you took the mean of those
No, I'm not taking a mean. I'm just putting all of them together and then finding the probability distribution function. It's similar to what we did here. Here you have 76 trials, right? Here you will have a much larger number of ISIs, because in each trial you are expected to get more than one spike. So you just combine them and then find the probability mass function. Okay, and that is what
Okay.
is shown here. Okay, you can look at this
But
code, get ISIs. It will tell you how to do it. Yeah.
here for whatever you want to design the interspec interval, we need to define a time interval first. So how, like, from where do we start? Like from 240 to 280, or like 240 to 250? Like how do we decide that? Like for a
Time
given time.
interval. I don't. What? Say that again. What do you mean by its time interval? Are you talking to this
So
time
like
interval minus 0.32 minus
yeah yeah
0.0?
yeah
Yeah.
yeah.
So I am looking at the ISI distribution between these two time points. I could have done it at a different time point also, but this is how I have defined it because I see that the firing rate is not changing during those intervals. And my question is based on that within this time interval, is it firing using a rate code or not?
Oh, okay, got it.
Yeah. All right. So let's move forward now and talk about correlations. Okay, so this correlation business is actually very popular in the field, in our field, because whether neurons fire together in some way or their firing, firing of one neuron depends in some way on the firing of another neuron, uh, tells you a lot about the way neurons together encode information. Okay, so to understand how a group of neurons together encode some stimulus feature, you need to look at potential correlations between them. So this has been a topic of great interest since the early 90s, I would say. Whether where how the correlations affect neuronal information carrying capacity of the entire population has been studied at many different levels. Actually, simple correlation is easy to compute. It's a relationship between two neurons at a time. It's a pairwise comparison. I'll get to the exact definition in a bit. But even for an entire population, it turns out in the presence of correlations, the capacity of the population to encode something changes drastically. And there are lots of papers on this. I would refer to just this one paper here. It's something that explains our stuff very well. But the topic itself, correlation, is so common, so ubiquitous that you can just read Wikipedia and get a very good idea of what it is about. So in our data, in brain signals, you often find that firing rates are correlated, which means that on a given trial, if neuron 1 has fired more spikes than usual, chances are that neuron 2 would also be firing more spikes than usual. Okay, in a different trial, when neuron 1 is firing less spikes than usual, chances are that neuron 2 would also be firing less spikes than usual. Okay, so this is a case of positive correlation between the two. And it's expected because neurons often get a common input from the previous brain area. So remember, in primary visual cortex, information comes from the lateral geniculate nucleus, or LGN. So if the LGN neuron, which is providing inputs to all the neurons in V1, or many neurons in V1, so if that neuron in LGN fires more spikes, chances are that the downstream neurons in V1 would also be firing more spikes in that trial. So the common inputs would cause the neurons in V1 to fire in a correlated manner. Okay, so now the question is it good for these neurons to be correlated, or is that bad? Now, turns out it is actually a very deep rooted question. It's actually, not straightforward at all. And from an information theoretic point of view, people have worked out different scenarios in which correlations can either be beneficial or detrimental. But that goes fairly deep into information theory that I am not going to go over in this class. Uh, I'll just give you a very straightforward, or one of the first ideas that were proposed, which suggested that correlations are bad. I should mention here that there are cases where correlations can be good also, but for now we are just looking at a very simple case in which correlations are bad. And the correlations are bad because a simple strategy that you could just average the firing rate of a bunch of neurons that seem to be coding the same feature, that simple averaging strategy doesn't work in the presence of correlations. Okay, this is a slightly tricky point, so you have to think through this. So let's say I have presented, okay, so let's say I'm back here. I am just asking whether there's a stimulus or not. That's it. By just observing the firing rate of this neuron. So you will say, okay, it fires about 20 spikes when there is a stimulus and 5 spikes when there is no stimulus. So if the neuron fires more than 10 spikes, I'll say there's a stimulus. Otherwise, I'll say there's no stimulus. And that's a good strategy. But remember that this plot is the average of 76 trials, right? I average 76 trials to get to this plot. But the decision I have to take in the real life is based on just a single trial. You look at something and you decide whether it's there or not, right? Somebody's face in the crowd, whether it's there or not. You don't get 76 trials. So how are you going to solve this? Well, any thoughts? How are you going to solve this in the real world when you don't have this luxury of having multiple repeats? Anyone? How would you do this? See, in a given trial, the neuron might be firing just 3 spikes or 4 spikes. You have to take a decision based on just, 150 milliseconds. In that small duration, the neuron is only expected to fire, 20 spikes per second. So in 100 milliseconds, you're talking about 2 spikes. You have to make a decision based on the firing rate of over some very short duration. And the neuron can't fire fractional spikes. It's either going to fire 0 spikes, 1 spikes, 2 spikes. So how are you going to decide just by listening to this neuron whether there was a stimulus or not? So who has a good answer to this? Anyone? Can you guys hear me? Always wonder if I'm just talking to myself.
Yeah.
Yes, sir.
Yeah.
Yes, we can
We
hear.
can hear you.
So maybe if we look at neurons in the surrounding region, if they also have a similar spike, then maybe we could say that there was some sort of a stimulus.
Similar. Okay, so you're on the right track, but why do you want them to have similar spikes? Well, okay, so you're on the right track. So I'll give you the answer here. One simple strategy is that you make 76 neurons pretty much code the same thing. And what you do is just take the average of all of them and use that as an estimate of whether there was a stimulus or not. So essentially you don't look at the stimulus 76 times as done here, but you have got 76 different neurons that are looking at the same stimulus and you're averaging them, and the average ought to be closer to this. The more neurons you average, the chances of having a low average in the stimulus period is going to be lower, right? So you are essentially, it's a coding strategy. Lots of neurons, you average their responses, right? Now comes the question that if the neurons are firing randomly, is it better in that case, or is it better if the firing rate is correlated? Okay, it's a rather deep question. So keep that question in mind while I explain what correlation is to those who are seeing this for the first time. And then we will get to this question. Okay, and I will try to convince that in this simple decoder, which is just based on the averaging of different neurons, correlations can be bad. Okay, and not good. The neurons nearby shouldn't be correlated. They should actually be decorrelated for you to have a good estimate based on a simple averaging scheme. I'll get to why this is the case in a bit. Let me first explain what correlations are. But before that, I will show you some data from, well, this is not data per se. This is the result from a paper that showed that when the monkey pays attention to a particular stimulus, the neurons that are coding that particular stimulus decorrelate, which means that their correlations reduce due to attention. Okay, so this is basically a very similar setup as what I had told you. People recorded from a bunch of neurons simultaneously and looked at the firing rate. So the top plot here is firing rate. So the same stimulus produces a higher firing rate when the monkey pays attention to that stimulus. This has been known for a long time, that even the identical physical stimulus produces a higher response when you pay attention to it. What is shown here is that not only does attention increase the firing rate, it also reduces the Fano factor, which means that it reduces the variability in firing. Remember, Fano factor was the variability divided by the mean. So the variability reduces, the neuron becomes more reliable. And the new thing that is shown here is that the noise correlations that are present, forget the x-axis here, it's a little bit tricky to explain, so I will skip that part. But notice that in general, the firing rates are correlated. The y-axis shows correlation. So when the monkey is not paying attention, the line is higher. But when you pay attention, the correlations reduce. Okay, and how attention causes a change in correlation and the change in firing rate and reliability has been a question that has been investigated for a long time and still being investigated. Okay, the setups like these, this is where the fun is. You get data and you try to figure out how is it that the brain is, how is it that a complex a phenomenon like paying attention boils down to very detailed circuit level neuro physiological, how is it explained in terms of neurophysiological correlates. Okay, so so this was the motivation for us to study correlations, whether neurons tend to fire together or not. So in our data set, let us ask that question. I have given you two neurons and I'm now asking in our data set whether the firing is correlated or independent. I'll tell you what the difference is. And the second question is that when I present a stimulus, is the correlation or the independence changing in some way? Okay, so this is the question that I'm asking, and now I'm going to formally explain what I mean by independence and correlation, and we will answer that in that, and then I will answer why is it bad to have correlations, which will sort of explain why attention reduces the correlations. Okay, that's what we are going to do today. Okay, so independence and correlation. So again, I have asked a question, and now I'm figuring out the math that is needed to answer the question. Okay, so first I'll tell you what it means for two events to be independent. It's if the probability of the intersection is equal to the product of their individual probabilities. And in terms of random variables, two random variables x and y are independent if the probability that x and y take the value x and y each, small x and small y, is equal to the individual probabilities, product of the individual probabilities, or in equivalently the joint density function fxy x comma y is equal to the product of what are called the marginal distributions ffxx and f by y. We will see an example of this shortly. Okay, so this is the definition for two random variables to be independent. And correlation is a weaker measure. If two random variables are independent, their correlation is always zero. However, if correlation between two random variables is zero, that does not mean that they are independent. Okay, so independence is a stronger condition than correlation, and you define it this way. This actually is the covariance, but correlation coefficient is just the normalized version of it. So let's first see this. It's the expected value or the average of the deviation of x from its mean multiplied by the deviation of y from its mean. Okay, so why do you want to do it this way? What's the purpose of this definition? Can anyone tell me? Why did we define it this way?
Normalization
What do you mean by normalization?
means the value should be less than 1.
No, the covariance, we are on the top part here. The covariance is not between 0 and 1. No, I'm asking for an intuition why I want to do x minus ex multiplied by y minus ey and take its average value. So I'll give you the intuition. Somebody,
I always
yeah.
reasoned it out as like, I mean, like the variance, except now it's with another vector, which is also being
Yeah. But why do you want to do it this way? You're right that if you
I
if you
don't
replace
know.
x,
This is not the best explanation, but if y is equal to x, then it ends up becoming the variance. I do not know how that answers the problem, but it, yeah.
Okay, so let's think about what we mean for two random variables x and y to be correlated. Okay, so it means that on a given so I'm doing a random experiment and I am looking at x and y. So on some trials, every time I do this experiment, I get a value of x and a value of y. Now, if they are positively correlated, that means that in a trial or in one realization of that random experiment, if x happens to be larger than it ought to be, chances are that y is going to be larger than what it ought to be, right? Because they are correlated, positively correlated. So x minus ex is exactly that. it's the probable, well, it's not the probability, it's basically, so the random variable having a value more than its mean. So it's going to be a positive number on some trials and negative number on other trials. X is a random variable, so it's taking different values. The mean is fixed, right? So if X and Y are correlated positively, then when this number is positive, so is that number. So the product is positive. Likewise, when X is less than EX, so it's a negative number, chances are Y will also be less than EY because X and Y are correlated. So the product will again be positive. So the average value of the product is expected to be positive when X and Y are positively correlated. Likewise, if X and Y are negatively correlated, which means that when X happens to be larger, chances are Y is smaller than its value, then this product is always going to be negative. Okay, so this product therefore tells you how X and Y co-vary. And hence this is called the covariance. Okay. So that's why, does that make sense?
Yes, yes.
Yeah. So that's why we do this. Now the only problem with if you estimate this is that it really depends on the absolute values of X and Y, right? If I multiply X by 100 and Y by 100, then essentially, this number is going to get multiplied by 10 to the power 4. So it's not a measure, just the absolute value of the covariance really doesn't tell you much. So what you really need to do is normalize this by its variance, which is what you obtain by replacing X with Y. So it becomes E minus EX whole square, which is the variance. So if you normalize by that, then if I multiply X by 100, the numerator will get multiplied by 100, but so will the variance. So the covariance divided by the variance will give you something useful. It's not the variance, the standard deviation that we have to take for X and Y separately. And that is what is called a correlation coefficient. It's just the covariance divided by the product of the individual standard deviations. Okay, if I replace X with Y with X, then you will see that it will become 1, because the covariance of X with X is just the variance of X, which is sigma X square, and divided by sigma X multiplied by this is also sigma X, because Y is equal to X. Okay, so this is a value which becomes 1 when Y is X, or Y is very highly correlated with X. Likewise, it takes a value of -1 when X and Y are completely anti-correlated, and it takes a value of 0 when X and Y are uncorrelated. Okay, so it's actually very so this was the math part. Okay, so mathematically this is how you would find it. I will show you how to do this, but it actually pays a lot to think about this in a graphical way. And think about what independence and correlations mean in terms of, in a graphical way. So what you are seeing here in the top are scatter plots, essentially where each dot represents one realization of the experiment. So if I do the experiment 76 times, like my neural data, I'll have 76 points. And I'm just plotting the value of X as a function of value of Y. Okay, so in our scatter plot, so this is the, the joint scatter plot. This is how X and Y are together seen in a two-dimensional plane. So when X and Y are highly positively correlated, you will see that, whenever X is larger, so is Y. So they're falling on a line like this. Likewise, when they are negatively correlated, -1, then it's like that. And these are the cases where the correlation is falling. So it's 0.8. So the scatter tends to become wider, which means that it's no longer always the case that when X is larger, then so is Y. But in general, that is the case. Okay. Now, one thing that you need to realize that correlation, the Pearson correlation that we are talking about, it actually just depends on the scatter about this line. It actually doesn't depend on the slope of the line. Even this one has a correlation coefficient of 1, because again, X and Y are always, there's a very strict relationship. Whenever X is larger, so is Y. Right? And similarly, in this case, this is where the correlation is not defined, because the variance, the standard deviation of Y is 0. Sigma Y here is going to be 0, because it's always taking the same value. Y is always the same value. So its variance is 0. And these are all a bunch of cases where the correlation is 0. An easy way to think of this is that if you fit a line to this, it's going to be flat. So, there's no dependence on average between X and Y, like this one. The correlation is 0. But now we'll ask a more involved question, that whether the firing rate is also independent in this case or not. So if you look at the plots below, this is not an easy question. So really think hard and tell me what you think. Do you think, so suppose I do my experiment and I get the number of spikes, and I put the number of spikes from neuron 1 on the x-axis and y on the, neuron 2 on the y-axis. I get a scatter plot like this diamond shaped thing here. Can you say, and the correlation here is 0. Can you say whether they are independent also or not? Think and tell.
Could you repeat the question, sir?
The question is whether X and Y are independent when I show a joint distribution which looks like this, or looks like that, for example, or that for that matter. Just by looking at the density function, can I say anything about the independence between the two random variables, where independence is defined this way?
Intuitively, I think we cannot, because like we, we we cannot. But intuitively, I think that there seems to be some sort of independence, because in a way that diamond shape plot means that X is taking every value between the left point and the right point for some value of Y. So there seems to be some sort of independence, but not entirely.
Okay, well, so it's a binary thing. They're either independent or not.
Fair enough. Sorry.
So okay, so basically, when I say two random variables are independent, then when I tell you a particular value of X, it doesn't change. It doesn't give you any clue about what Y could be. That's when they are independent, right? So in this case, in the diamond here, for example, If I tell you that X is this extreme value, does that tell you something about Y?
Yes.
It does, right? It can't take any other value. It can only take this 0 value. It can't take anything else. So this cannot be independent. And you can actually look at the whether two random variables are independent or not just by looking at the density function. In fact, none of these guys are actually independent, because if I tell you something about X, it will tell you what Y is. This could be independent. This is the only one that could be independent. But these funky looking shapes are not independent. So let me explain what this matter, how the shape should be. So I'll do this. I'll do this in my in the data set that I have given you. So how do I compute the joint density? I'll get the spike counts. Okay, so I'm looking at whether the neuronal firing is correlated / independent in the baseline period. So remember, it will give me 76 numbers, one for each trial. So I get 76 numbers here. I get 76 numbers there. I plot XBL1 versus XBL2, and this is what I get. Note that because it can only take a few values, there might be a lot of points sitting on each of, there may be many trials in which neuron 1 fired 1 spike and neuron 2 fired 4 spikes. So there will be several points sitting over there. There are a total of 76 points, many of them riding on top of each other. This is how the scatter plot is going to look like in this case. It's not looking very impressive because it's only taking discrete values. Now I can count the number of times each pair is observed. So, firing neuron 1 firing 0 spikes and neuron 2 firing 1 spike happened 4 out of 76 times. Okay. So if I want to color code it, this is how it will look like. Neuron 1 firing 2 spikes and neuron 2 firing 1 spike happened 7 times. That's the most likely thing. So is this one. Given this, how do I now compute whether neuron 1 and neuron 2 are firing randomly or not? Sorry, that's not the question. The randomness is taken care of in the previous one. Randomness is the property of a single neuron. Here I am asking about independence. So I've got the joint histogram. So I'm asking you now, how do I proceed from this? Based on this information, can I conclude whether they are firing independently or not? What do I do now? This is all the data you're going to get. I mean, all the answers are in this data. How do I proceed?
Can we look at it? Can we look at the time scale, like let's say two the neuron 2 fired at 7 times, sorry, neuron 2 and neuron 3 has like fired for 7 times. So we can look at the time at which they fired.
Yeah, so we will get to that part in a bit, where we are looking at autocorrelation functions and cross correlation functions, where everything is done as a function of time. Right now, that's not the question. The question is, over this 200 millisecond interval, if I just look at the spike counts of neuron 1 and neuron 2, that defines two random variables XBL1 and XBL2, are they independent or not? We'll get to your question in a bit, but that's not the question right now. Based on this, how will you answer?
Should we see the correlation covariance basically?
Okay, but why do you want to look at the covariance?
Because then we'll come to know whether they have some correlation or not.
Well, if they are not correlated, doesn't mean that they are not independent.
That's right.
So we can calculate the joint density that when the values are taking that x is
This is the joint density. What you
yeah.
see
So
on the
in
left
that
side
case,
is the joint density.
in that case, we can compute the individual, like suppose the neuron one taking firing one time and neuron two firing for two time, and then compute their product and checking it, then verifying it with the help of that relation between the relation for that independence.
Okay, so very good. Now, how will you compute the marginal probabilities, marginal distributions? So give me from this, tell me how you will compute the marginal probability of XBL1 taking these values.
We can calculate it by counting the total, since we know the total number of trials, and we can compute the number of times that variable is taking that particular value.
Okay,
Say
so
0.
tell me XBL1 taking a value 0, what will it be?
Adding all the columns.
Just give me just give me the number.
4 plus 3 plus 3 divided by 76.
What is that? 10 by
10
76.
by
Right?
76.
That's right. So that's what you do. So you're counting how many times you're getting 0, 1, 2, 3, 4, 5, 6, and it's just an addition. Column wise, you add up all the rows here, and this is what you get for each column. Likewise, you can add up all the entries here for each row and get a value there. Okay, and if you divide by 76, this gives you the marginal distributions of XBL1 and XBL2. Okay, and if XBL1 and XBL2 are indeed independent, then the joint probability, which is again what you fill for this entire one, is just the product of the marginals. So XBL1 taking 2 and XBL2 also taking 2 is just you get that by multiplying 16 by 76 multiplied by 21 by 76. Okay, and this is how it's going to look like under that assumption. Number of times each pair is expected under independence is just the product of the marginals. This is what it means. It's very straightforward actually. Okay. Now, this should actually tell you a lot about how the joint distribution should look like under independence. Because essentially what you are doing, look at, think about this. You've got a vector here, which is these values, 7 by 76, 24 by 76, 16 by 76, blah, 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 blah. This has a particular shape. That's the marginal distribution. And all you are doing on this particular row, you are just multiplying by that shape by 10 by 76. So it retains the same shape. It's just a scaled version of that. See, it has this sort of a shape. And every column is just a scaled version of the same shape. Scaling factor being here. Likewise, if you look at any row here, so this has a particular shape and every other row has the same shape, it's just multiplied by some number here. This is why if I tell you that XBL is equal to 2, the probability of XBL1 given XBL equal to 2 has the same shape as XBL2 given, the probability given XBL2 is 0 or 5 or 7. My knowledge of what XBL2 is doesn't change the probability of XBL1 given the value of XBL2. This is what I mean by independence. Okay, so the joint density is always actually square-ish in shape. You're always multiplying two vectors. Okay, so it's got a particular marginal density, and the marginal density just gets multiplied by some value on the x-axis, and that's what you lay out, and that's how you get it. So trivially, you cannot have any of these shapes if the random variables are indeed independent. This last one, the one where it is rectangular-ish, this is the one that could be independent, but not the other ones. Does that make sense? Okay, here long pause here. So is this okay?
But I mean, all it's just telling us is that it's not independent, but nothing more than that.
No, it's not telling you that. So this is experimental data.
Yes.
This is what I expect it to be based on independence. So then my question is whether these two are indeed different from each other or not. And that becomes a statistical question. So what you do is you look at the observed entries. So each of these entries minus the expected that you get here, you square it for reasons that I'm not going to go into, and you divide by the expected one, and you add for all these values, and you get a number. And turns out this number has what is called a chi-square distribution. So in this course, we are not going to deal with statistics, but this is the chi-square test of independence, where you essentially are asking whether the observed ones and the expected ones are sufficiently different from each other or not. If they are, then this chi-square is going to take a large value and the test will fail, and you will say that it's not independent. Okay, because the observed one will always going to look like this. There's no way it's going to look smooth like this, right? So if here in this case, they actually look quite similar. If you notice that they are not looking that different actually. But this is a statistical test, whether they are significantly different from each other or not. And there is a test that does it. It's called the chi-square test of independence. If it depends on how many n's you have and what's the expected value that you expect, blah blah blah. But you do the test and it will tell you whether the XBL1 and XBL2 are independent or not. Okay, so that's the way you answer the question. So I'm not going to talk about statistics in this course. We already dealing with a lot of concepts. So statistics is one thing that I'm going to leave. But this is what you do to answer the question whether XBL1 and XBL2 are independent or not. And from what I remember, if you do the test, they turn out to be independent. They look quite independent actually in this case. Okay. This is what the joint density that you get when during the stimulus period, and there you could also do the test, chi-square test of independence, and that will give you answer. Here we look at correlation coefficient, which is actually straightforward. It's just this equation, these set of equations. So you compute the mean of XBL1. This is just one number. This is one number, M2. XBL1 is a vector of 76, right? So that minus M1, this is a dot product, which means I will take a point by point product and I take the mean, that is covariance, and I divide by the standard deviation to get the correlation coefficient, the same number that I had talked about here, this thing. This is how you would mathematically do it. And during baseline, it comes out to about minus 0.03. So, looks like it's quite uncorrelated. During the stimulus period, it seems that there is some correlation. You can see that on trials in which this one is taking like 12, odds are number of spikes in neuron 2 is also slightly higher. You see a slight, but it's a very mild correlation. The command in MATLAB that computes the correlation also does a statistical test and gives you a p-value. So you can also like say whether this number is significant or not for you to reject the hypothesis that they are uncorrelated. I'm again not going to talk about the statistics part, but this is how you would answer the question, whether they are correlated or not and whether they are independent or not. Okay, so any questions on this?
So for the correlation, just as you have mentioned here, to take its significant value or not, is it only the p-value test or just looking at the correlation value, say like 0.2? So what is the minimum correlation that one should see? Like it's
Yeah,
like
so it depends on how many points you have and a bunch of other things. So for example, well, so yeah, there's no example really. So just by looking at the number, you can't say. Even this could be significant if there are like millions of data points. So there's no one number that you can, use to get to this. You have to do a statistical test as well to determine whether this number is significant or not. Okay, and as I mentioned, it's there in the code that MATLAB uses. I am doing it from first principles here, but there's a core coif code which also gives you a p-value. So it will give you both R and P. And it does a statistical test and gives you the answer. If you're interested, you can find out what that test is. It's not something I can cover in this course because it'll take several classes to get to the stats part then. So just, you have to take this on faith. Okay. So let me then finally just mention the one part which I had talked about, which is this. So why is it that correlations are bad in a coding scheme where I'm just averaging the responses? See, the point here is that suppose I want an average when a stimulus is presented, I want the ensemble to fire 10 spikes. Let's say when there is no stimulus, the average firing rate is 3. When there is a stimulus, the average firing rate is, let's say, 8.5. Let's say. Now, what I really want is that each neuron is firing with an average of 8.5, but following a Poisson distribution whose mean is 8.5. So some neurons will fire more, others will fire less. If I have lots of such neurons and I average them, I should end up getting 8.5, right? That would be good. But this means that in a trial, I really don't want a situation where if one neuron is firing 12 spikes, all its neighbors are also firing 11 or 12 or 13, some large number, something that's greater than 8.5. Because in that case, when I average all of them, I won't get 8.5. I'll get 10 or 11. Likewise, in a trial in which one neuron fired 6 spikes, I don't want all its neighbors to also fire fewer spikes than 8.5 because then averaging won't work. Right? Does that make sense? For the averaging to work, I want them to be independent so that when I average, I get a proper estimate of the average. And I won't get that if the neurons are correlated. So in this very trivial coding scheme, when I'm just averaging the responses, I don't want correlations to be high. And this is what attention does. When a monkey, or for that matter, when as you are paying attention to my class, your neurons in V1 are getting decorrelated, so that the ensemble actually carries more information under this very simple coding scheme. Okay, now people have shown that if the coding scheme changes, correlations can be useful. We won't get into that. It becomes more mathy and more sort of involved than what it is. But think about it, from a larger perspective, that it's quite awesome that just by, recording from, like 100 odd neurons from a visual area, you can actually ask very involved and very detailed questions about how a cognitive mechanism like attention is playing out. Okay, what is happening at the neuronal level? We have access and we have, ways to address these questions. How is it that the brain is coding information? How is it that the brain is transmitting this information to other brain areas and things like that? Okay, this is what makes neuroscience so much fun. Okay, I'm done for today. So I'll again stop and take questions at this point. Let's stop recording now.